Okay, so we've been going over integrals just because we have to, but today is when we finally learn about its applications and what that really means for us. Oh, impossible! How could we do math with any meaning behind it? Well, not to worry. That's exactly what today is. So, why don't we get to it, to this guy right here?
Whoa, my goodness!
What is all of this? Well, not to worry. We just need to know exactly what each individual part means, but it's more in the sense we need to know what this looks like in our work. Thankfully, we should already know exactly what all of this on the right side of the equation is. Well, it's not like we just spent all of the last time talking about it with the definite integral. Thankfully, right there. But of course, we're trying to equate that to all of that craziness that is over there. So if we were really to break it down, and only just the parts that are the most applicable to us, yes, indeed, we have a limit as n approaches infinity, and now we have this Greek symbol of sigma right there, meaning that we are adding up or doing a summation of what though? It's going to be a summation of this, the function at x sub k multiplied by the difference of the x values of x sub k. I know this looks quite a bit confusing for many of you, but if we really thought about this, right, if the function values being the y values outputted from a function, think of it as a set of heights and then multiplied by a change in x being across the x-axis of the graph, multiplied by some sort of base because we are looking for the changes in that x. A base times a height sounds awfully like an area of a rectangle, doesn't it? Oh yes, indeed. That is exactly the way that we're going to do the next part of our integration solving, by actually understanding it as an area. But who cares about area? What do you mean area? That's geometry. Throw that in the back. No. The whole purpose of integration for us now, in the most applicable sense, is actually understanding the area underneath that function. Ooh, what could that mean for us? So let's take it to something like this, a very simple function around something like this, where we have the function f of x listed as such. But to show a little bit of emphasis here, what if instead we swapped the colors a little bit just to get an idea of what this looks like, right? Think about this, right? We're adding up all the different types of function values. Again, that is the height of that function. We're going to multiply that, as you can plainly see there. And then we're going across some change in x, right? So that is the delta x down at the bottom, if I can write that properly. And then we have the f of x sub k right there on the height. And so by going across that, would you look at that, we have an actual subset of an area underneath a function that we can easily calculate. Ooh. And so if we went all the way from the limits from a all the way to b for the function what we're going to calculate, imagine if we added everything up underneath that curve for us to then calculate as a singular number. Oh dear. And we have stumbled our way into understanding what true integration looks like as area under the curve. Yes, indeed. That is the whole purpose of definite integration, is that by evaluating at limits from a to b, we can then determine what is the actual area underneath that curve because we added all the way up through from those limits that we set before from a to b. Not so bad. So then what will it look like then for us with some actual example problems, right? So let's go through one quick scenario here as to what that might look like, okay? And at least for us, again, today we're gonna deal with just the rectangular basis, and there are some other methods that the AP test will employ. But let's have another look at a different kind of graph here. Okay, so let's see what that looks like for us on the easiest sense here. So we have that graph. Let's say we have a very nice linear function right there. Okay, so let's say we want to start adding up the area underneath this curve, again, maybe ending with that right there. Okay, so with that, if we were to make rectangles going across different parts of the function, as you can see, there you go. We have 3 distinct rectangles, at least the way that we arbitrarily did it right there. And of course, being rectangles, they're very easy to add up on the areas. But wait a minute. You might notice, excuse me, I actually see that you are missing some areas over there, and so it's not very accurate, and we should just integrate instead. Thank you for noticing that there are small gaps in between there. The whole purpose is that it's called for us an approximation. Okay? It is a way for us to get an idea of what the actual integral looks like, but this also means that this could be done if we never had the function to begin with. If we don't have an equation, we can use the graph with some approximation methods and get to at least some answer where if the function wasn't there to begin with would be a problem. Now, that also leads to, with your comment that you so graciously gave us, is that that's partially why as to we have this right there as the first part of the definition of definite integral, is that we are reaching an end going to an infinite number of subdivisions for all of the different types of areas that we're adding up. So how about this? What if instead we cut this down so we have now even smaller but distinct rectangles from the previous one that we have added in? Oh, would you look at that? We are actually decreasing the area of missing spaces that we have. Now again, let's have our imagination take over. What if we then continue to subdivide even more? Oh, we are then, with more subdivisions underneath the graph, we are actually getting closer and closer to a more accurate version of this approximation. Of course, that means up to a certain point, if we integrate, or at least in this case, subdivide those areas to an infinite degree of them, we will get approaching an actual value that our integration rules will match. Wow, who knew that math can be that sophisticated? I know for us, many of us, it does not matter. We will just go right on ahead and they go, where are the example problems? I just want to get this over with. Fine. We'll get right to that. It's just, I thought it was pretty cool that the whole purpose of approximation is that eventually, if you kept going with the subdivisions, you'll eventually reach something close to and reaching the actual definite integral, which kind of is the way that many computers do integrals today. But nonetheless, though, let's go ahead and see what that will look like in terms of an example problem. We'll go over 2 methods of doing these types of summations. There are actually 4, but we'll go 2 at a time, once here today, and then the last 2 tomorrow. And so with that, let's swap over to maybe something that looks a little bit like this, where this is indeed quite the large example, but nonetheless, this will illustrate to us in better sense what a Riemann sum looks like and how we can get to some easy answers. So it says here that we will approximate the integral going from 0 to 2 of x cubed dx by using 4 subintervals of equal width, and then calculate by first the left Riemann sum and the right Riemann sum. Now we'll get to what these mean of using left and right, but first, why don't we go and use a table here to then describe those intervals, again, where we need to know base multiplied by height. So a table would be the best way of really listing all that out, and we could even have a graph over there to make it show what it looks like visually as well. So over here, I'm going to write for ourselves the x and y values for this function here, the function being x to the third. So at least for what I'm going to do, we'll start with going, because again, the limits are from 0 to 2, but you might see here what this looks like on this sense. So we'll go from 0. Of course, the resulting is a 0. But going forth, I'm actually going to go with 1/2, 1, 3/2, and then 2 as the actual points of x. Now you might be thinking, why did he do that? Well, you might notice here is that they're asking for 4 sub-intervals. They want 4 of these guys with different rectangles. If you took a look here, going whole numbers from 0, 1 to 2, now that won't work. How can you get 4 subintervals, 4 rectangles with only 3 x values? Doesn't work, sadly. So we actually need to split that in half, because again, they did say also we are doing equal widths, so the distance must be the same across. So if we want a distance of 1/2 every time instead, we can then reach 4 rectangles with 5 points. Sounds pretty nice to me. So let's continue though. 1/2 raised to the 3rd power. Again, some simple algebra here makes it 1/8. 1 to the 3rd power is still just a nice 1. 3/2 to the 3rd power. Again, keeping up with what we can do so far. It's 27/8, keeping everything clean with the fractions. And then 2 to the 3rd power is now a whole 8 instead. Okay, very straightforward as to getting a table of values that we will then reference back to when we're actually calculating some summations. But now let's have a look at what the actual graph will look like. So let's see here if we can put that together. And again, something very simple here. Okay, we'll understand that this is a x to the 3rd power function. So we'll just go ahead and do 5 different points here. So 0, 1/2, 1, 3/2, and then 2, that is. 8 will be the actual height. So we do need to go up 8 times, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to the top. So we have 2, 8 that we started with, and then 0, 0 that we also started with. Okay, 1, 1 as well, and then 3/2 with that 27/8 would be somewhere around between 3 and 4. So we can go do that. So we end up with a nice curve like this for the function. All right, very nice. And so we'll switch over to see what that really looks like for us when we are then calculating the left Reimann sum. All right, so what does those directions mean for us when we do these types of approximations? Well, if we're doing the left sum, again, these are the left side points where we can then determine where the rectangles are. As you can see, we have listed out 5 points here, right? That's quite a few, but we need to still draw 4 rectangles from it, right? So again, we think of it as rectangle base 1, right? Because from 0 to 1/2, then 1/2 to 1, and then 1 to 3/2, and then 3/2 to 2, right? That's how we base out 4 rectangles from 5 points. It's the distance from one to the next, right? And this is where you might notice where the left comes in, because if we have 2 different x values, those are 2 different y values. What? We can't get 2 different heights? Exactly. With only 1 rectangle to make from 2 x values, which one will we choose? Will we choose the left number or the right number? And would you have it? That our heights of going 1, 2, 3, and 4 are going to be the left side points to add up with the left Reimann sum. Then, of course, going to the right side, let's denote that R, are going to be the 4 right side points instead. How intuitive. Very good. So let's go ahead and start adding these up. Again, this is just simple rectangular addition here of just finding the areas of each of these guys. So thankfully, because 1/2 is going to be the base across each of these guys, okay, again, this is going to be for the left. Okay, we're going to go across with 1/2. Again, the bases are all the same, so thanks to distributive property, it's just going to add up with the same base multiplied by all the different heights. So heights are going to be 0, 1/8, 1, 27/8 lastly. Okay, very nice. So again, the 1/2 would be distributed to every single one of them because it's the height times each individual base. Thankfully, because it's the same exact base, we can leave it out for later, kind of like coefficient rule. Isn't that wonderful? So we get to go ahead and start putting things through. So we have 1 over 16 plus a 1/2 plus, in this case, 27 over 16. Okay, we can add these up together. So this is going to be 28 over 8 for the common fractions with the common denominator. That's not an 8, that's supposed to be 16. Okay, and then that 1/2 is going to match that same denominator as 8 over 16. And so we end up with 36 over 16, which would then result in, if we simplify that, as something along the lines of 9 over 4. Again, this in this case will be the left Riemann sum for the result of us adding them. Okay, so let's see if we can imagine that on the graph here, right? We have the rectangles matched now from 0 height, the first guy, then the 1/2 height down there, and then the 1 height over here of 1, 1, and lastly the 3/2 height over there. All right, see, as you can see, we have the 4 rectangles. The first one is just a 0 height, so it has no area with a height of 0. But we do have the areas that we did add up for, and it looks pretty good. Okay, so from here, let's see if we can get to the right Riemann sum and calculate that instead. Again, going with the right side heights that we listed out on that side instead. So the same idea is going to happen, that we have 1/2 as the common base. We just have to add up each of the individual heights at 1/8 plus a whole 1 plus the 27 over 8 and then plus a whole 8 lastly as the last height in our table there. And so before we distribute that 1/2, we can combine the like terms here inside the parentheses, which makes it 28 over 8 and then a whole 9 after that. Okay, then we can go ahead and start slamming in that 1/2 across the board, which makes it 14 over 8 plus a 9 over 2. Okay, and so with that, we can just easily match the same denominator for that 9 over 2. So it becomes 14 over 8, adding with a 36 over 8, which then gives us a whole 50 all over 8, which then simplified will give us something along the lines of, it was 6 and 2/8, which is going to be 6 and 1/4. Okay, fairly nice. Okay, so again, the right Riemann sum that we just calculated for is 6 and 1/4 as its area underneath the graph. Very nice. So let's finish this off by looking at some of the actual areas for that. So again, now we're going to go from the right side, making rectangles this way, and then ending all the way with the 2. And as you can see, in comparison, it looks like the right Riemann sum goes over the graph, as you can see on that side, right? With taking the right points and going across and making the rectangles, we have gone over the actual graph itself and went kind of beyond, in the sense of approximation, the actual integral itself. So what we can say here is that because the left Riemann sum was under the graph, the right Riemann sum ended up with the rectangles above the graph. The left Riemann sum is an under approximation, and now the right Riemann sum is an over approximation. Okay, so we'll do a final comparison. We can save all this data for next time, as we will go over the next 2 methods of finding the Riemann sum of any kind of function. But with that really should wrap up for just today's lecture about this. Again, we'll go right into the other example of 2 other ones tomorrow, along with actually comparing it with the correct integral and seeing where this leaves us with some other problems. All right, so that's quite good. And again, as always, you can always email me at my email, thelabcoatmath@gmail.com. And you can always see us again on the live streams. There will be one tomorrow on Thursday. Again, the times are 4 to 7 p.m. PST. And we'll be able to discuss anything else you'd like to have live if you have questions there. Once again, thank you all for watching, and we'll see you next time.